Okay, the next thing I want to discuss is what I call the back door. Okay, the back door does not use the CAN bus. The back door uses an interface to the module called the BDM. Okay, I've written it sideways here, BDM. So, sorry, like I said, my art is just not great. And BDM stands for Background Debugger Mode. And what is that? Okay, and why is it different than CAN bus? All right. Well, the background debugger mode, or the background debugger technique, originated because when engineers were designing their modules, what they needed to do, I mean, you just don't sit down one day and write a whole bunch of code, download it to your module, check it out, everything works exactly the way that you expected it to, and then you ship it off. No, that is not what happens. Okay, what happens is you write your code, you download it to whatever your circuit is, and then you run it, and then it doesn't work, or it works like it's not supposed to work, because it has what are called bugs. Okay, that's where you write code that's supposed to do something and doesn't do it, and then you got to go and figure out why it didn't do it. All right. Well, initially, the way that microcontrollers allowed engineers to debug their code on a microcontroller was the microcontroller would allow them to upload upload their code into the RAM of the microcontroller, and then they could run it. Well, the RAM wasn't big. So what they would do is they would write little chunks of their code, upload it to the RAM, test it out, get it working, and then they would write another chunk of their code, upload it to the RAM, and get it working. And then by the time they had all of their chunks of code working properly, they would link them all together, program all of that into the program memory of the microcontroller, and then, test it to confirm that it worked. And that's how it was done initially. Well, the problem with that approach was that in order to upload programs into the RAM of the microcontroller, it takes external pins to support transmit, receive, reset, and other, conditions in order to communicate with the part. This is what our product does with the ACOM. Okay, ACOM is asynchronous communication. We, in order to communicate with some of these microcontrollers, will upload our communication program into RAM and then run it, and that's how we're able to access the EEPROM. Okay, and program the EEPROM. It's by a program that we send up to the microcontroller. Anyway, that became kind of encumbering when it came to, sending up, debugging larger amounts, debugging larger pieces of code, plus it used more pins. That you want to, when you design a microcontroller, you want to be able to use all the pins that are on the outside of the package to do control things. You don't want to have those pins be dedicated to uploading programs into the microcontroller. You would like to test your program with all of the functional pins of the microcontroller. So they came up with a technique which is really slick. It's also really complex and and very sophisticated, called the background debugger. Okay, the background debugger mode in most cases will only use a single pin on the processor in order to get data to go in and the data to come out. Okay, but here's the thing that is really interesting about the background debugger technique. The background debugger is built into the silicon of the processor. Okay, meaning it's not part of the processor's program. Or you put it on a background debugger based tool. What happens is the background debugger tool will actually go in. It sends commands onto the silicon of the processor, but they're not program commands like the processor would be normally running its program, being whatever it's being. It will still do that. It will do it it will do it as part of its normal operation. But in the background, the background debugger can send a command to the background debugger hardware on the silicon, which will do something like examine a memory location, write a memory location, things like that. This is happening in the quote-unquote background while the program is running. Okay, so it really facilitated debugging of microcontroller code and made it far, far better than just uploading little chunks of code and debugging that way. Okay, well, since you've got the option in some of the larger, processors of using the background debugger function, because it's built in anyway, okay, you can invoke background debugger commands to go in and read and program, okay. The other thing that you can do with the background debugger is, since you are directly controlling in the background, you can directly control the pins of the microcontroller. Okay, what that means is, even though, let's say you've got an external EEPROM, all right, the background debugger is capable of reading by manipulating the pins on the processor, because it's doing it in the background. It can actually read the data from the EEPROM using background debugger commands and not even affect the normal program of the microcontroller. It's an incredibly powerful feature in order to do, to do reading and programming. Also, if you use the background debugger, and if you see how the background debugger works, okay, basically the background debugger, I've drawn here 4 lines. Usually, in reality, you should only need ground, power, and usually 1 pin to put it into background debugger mode. And then you need the background debugger pin, because the commands go into the background debugger. They're fast. They go in real quick. Okay, you're not dealing with CAN bus kind of slow. You're dealing with operating frequency of the processor speed, because it actually, there are things called cycles that sequence through logic in the microcontroller as it runs its program. Background debugger will use a technique called cycle stealing, and it will actually take a cycle, pause the processor briefly, do something in the background, and then let it go. It's really, really neat. Anyway, that's what the back door is. Okay, you don't need to be hooked to the CAN bus. However, if you look at what's required in order to get the background debugger to function, a lot of times you'll see them, they'll mount the circuit assembly will have little pads on it, and then you mount it into what's called a frame, and then the background debugger probes come down and they touch the pads, okay? That's one technique. The other technique is you solder wires. You solder wires onto certain specific points on the assembly, and that allows the background debugger to function if you don't have pins. For example, if you have a module which you're going to reprogram, and it's small, it doesn't fit into a frame, okay? Frames are primarily used for ECUs, not other modules. But you have the ability, because it's built into the processor, and not all processors have background debugger. Don't misunderstand me. It's not there in many, many processors, especially the little ones, the smaller ones, the 8-bit ones, because it's costly to implement that function on the silicon. So they don't do it, okay? They'll just program it, when the part is fabricated. They'll put the program, whatever the module is supposed to be, in the part when it's fabricated. But if you've got the background debugger capability, then you have the ability not only to read at high speed, you can program at high speed, and this is how the people that do the tuning, okay? I guess you could do the tuning by sending commands over the CAN bus, but it would be very lengthy. If you got a background debugger, you can zip that data into the flash memory, and it's real fast. Problem is, background debugger is not very convenient, okay? Believe me, dealers and other techs, they don't normally use the background debugger, but that's why I call it the back door, okay? And I want to cover a couple of other things with respect to the background debugger. Okay. If you, as I said previously, have a failed flash update via the CAN bus, via the front door, okay, something fails, all right, and there you are left with a brain damaged ECU because half of its data is not available, okay, or is corrupt, and it won't work. Basically, as far as you're concerned, it's a throwaway module. With the background debugger, if you have the original code that went into the module, okay, and one way to get the original code would be to go buy a brand new virgin module from a dealer, hook it up to your background debugger tool, and read it, okay? And then you can save that file, and in the event that somebody, you know, corrupted their ECU flash because of a failed flash, you could, with the background debugger, reprogram the flash memory because it doesn't use the processor. The processor has to work, meaning the electronics has to work, but the program doesn't have to work because this is all happening with hardware in the background. All right? So that's what the background debugger does, and that's how the background debugger works. It's a totally separate function built onto the silicon of the processor. So you don't have to worry about sending commands over the CAN bus in order to get something to happen. But, as I said, it's not as convenient to use the background debugger, but it's a very, very powerful mechanism by which you can go in and, you know, recover or read or program, and you can actually access an external EEPROM simply by allowing the tool to manipulate the pins on the processor, which control the reading and programming of an external EEPROM. So it's a very powerful mechanism by which to do module work. All right. So that is the back door. I wanted to cover that. All right. Okay, I covered the front door. I covered the back door, and I neglected to cover another option called, I'm going to call it the side door. See, I call it the side door. And the side door, it's an interesting interface, and I'll explain to you how it works. And it's entered using what's called boot mode. Okay, well, I referenced, you know, how programs in a microcontroller, you have the flash memory, you've got the actual processor, you've got random access memory called RAM. Anyway, that's what these pieces are here: microcontroller, RAM, flash memory, and EEPROM. Okay, but the thing that's different about this approach, okay, it's not BDM. Okay, it doesn't have special hardware or special electronics on the silicon that allows access to things. The way that this mode works, it's a processor mode, a special mode of the processor, which the processor will enter, okay, if it recognizes that there is a specific logic level on a pin on the processor, okay, and that pin is called the boot pin. Okay, well, if you watch videos of people that are using a tool which requires a logic level applied to the boot pin, you see a probe which is going down or a wire soldered on or something like that to a boot pin. And it's just a separate pin on the processor, and its purpose, okay, is to, when the processor starts normally and there's no connection to the boot pin, the processor will start executing its program, which is stored in flash memory. Okay. However, if there is a logic level, and usually it's a ground level, a logic 0, on the boot pin, then the processor will enter what's called boot mode. Okay, well, what does boot mode do? All right. Boot mode will allow an external program. Okay, this is not a program that controls the vehicle. It's not a program that does anything specific to the car. What it is, it's a communication program, communication and control program. All right, and what it's written to do, all right, is to actually manipulate the areas within the microcontroller. Okay, the flash memory, it can read and write flash memory, it can read and write the EEPROM, it can control the I/O pins. The difference is this is a program that's loaded in boot mode, and it's loaded into the RAM, okay, of the processor. I've drawn the RAM outside of the processor just as I've done the flash, because it's easier for me to represent what I'm trying to convey by having these boxes outside of the microcontroller. But in reality, depending upon which microcontroller the design team uses, the flash and the RAM and perhaps the EEPROM also is all on the silicon of the microcontroller. Okay. But the point is, a program, an external program, was written, and the purpose of that program is to allow direct control of flash reading, flash programming, EEPROM reading, EEPROM programming, manipulation of I/O bits to control, whatever they would choose to exercise. But the way that it is entered into RAM, okay, is through the boot mode. Once the processor is in boot mode, it will start looking to see if data is coming in. In this case, the CAN lines are typically how this is done, okay? These are not CAN bus commands, okay? These lines transform themselves into basically transmit and receive pins, okay? And the way that it works is you have to have synchronization, because the bits that are now flowing over these lines have to be synchronized with the receiving circuitry that's in the microcontroller. Okay, and what I've shown here is a signal called clock, and the clock signal basically synchronizes the bits as they come in. Okay, in this case, maybe I should mark this. Let's say this is transmit and receive. Okay, so what's happening is bits are flowing in over this CAN line. It could be CAN high, could be CAN low. It depends on how they implemented it. But those bits are actually program instructions, which are then loaded by the microcontroller into RAM. Okay, so there's an external program which is designed to do all of the reading and writing and bit manipulation and all of that, which is part of the tool, okay? But in boot mode, it gets brought in over a communication line, which is normally a CAN line, but it's not a CAN command, okay? Think of the CAN command as something that only works when the processor is running, its program, and it's being, performing its function as the controller of whatever it's responsible for in the vehicle. Okay, in boot mode, this line becomes basically a receive line and a transmit line. Okay, and in order for those bits to be processed properly, I'll try to draw it here so perhaps you can understand better. If you have bits coming in, this is a low, this is a high, this is a low, this is a low, 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 this is a high. Okay, there has to be some way. This is a 1 state, this is a 0 state. There has to be some way for the processor to know that at this particular point in time, it has to, right here, it's got to sample the logic level coming in on the transmit line or the receive line, and put a 1. So it might sample here, sample here, sample here, sample here, and then it gets over here and it samples here, samples here, samples here, samples here. And that's how it knows, to take an instruction and break it up into a bunch of ones, and then 0, 0, 0, 0. It then takes those groups of bits as they come in, and the data on the transmit or on the receive line is going up and down. It has to be synchronized by another signal, okay? And the signal that synchronizes it is called a clock. So if you see a line hooked to a pin on the module connector called clock, that's what it's doing. That's its purpose. Now, depending upon which processor they used and whose module it is and all of that, sometimes the clock can be actually, you'll find it on another CAN line, okay? But the whole purpose of boot mode is to allow a program to be uploaded from the tool into RAM, okay? So the RAM is now going to contain a program, BDM, okay? And that program, purpose of the program is to, once again, read and write flash, manipulate bits on the module, access the EEPROM, whatever, okay? But it's a separate program which runs in RAM, all right? And as long as the module has power, that program will continue to run, and that program not only manipulates, the circuitry in the module or on the processor, it also communicates back to the tool, okay? And so on this line, you're going to have data that's coming in, okay? And you're going to have data that's going out. Okay, so this is in from the tool, out to the tool. So the tool will say to the program running on the RAM, give me the data, the byte that's at address whatever in the flash memory, and then the little communication program will read that particular byte from the flash memory, and it will pass it back out over the communication line. Okay, this, when you only have one wire, one line that does this, it's called half duplex. Okay, I'm just giving you some behind the scenes information. Half duplex. Duplex. That means it's a shared line. Data can either come in on the line or it can go out on the line, but it can't both of those can't happen at the same time. However, depending upon the controller, how it's configured, and all of that, the other CAN line can be used. You can have one CAN line which allows data to come in, and another CAN line which has data that goes out. So you have two wires, okay, which allow communication. That is called full duplex. And full duplex is going to be faster than half duplex because you have data that can go in both directions at the same time, as opposed to half duplex where data can only go in one direction at a time. So this would be faster. The reason I'm pointing this out is you can make these connections without opening the module, okay? And if you look at a tool which is using boot mode to communicate with a module, you'll see that they have connected wires to CAN bus. Usually you might have a clock wire. They might use the K line. I mean, there's not a direct standard for the way that this works. Every one of these is different. Okay, they're all different. But that's a mode. That's what boot mode is. And boot mode, I decided to call it a side door because a back door is what BDM is. Okay, BDM is directly accessing the flash memory, the RAM, I/O, EEPROM through a hardware interface. Okay, boot mode does it through a software interface. The software interface is the program which is running in RAM, which was uploaded from the tool into RAM, and then the way that it works is when the tool first starts, and you select the boot mode on the tool, the tool will then, based on the processor that you've chosen and any other parameters which you have defined, the tool will select the right communication program, and it will send it up to the processor, which then sticks it into RAM. And then once it's done, it basically once the program is fully uploaded, the processor will start executing the program in RAM. Okay, so it uploads and then it starts executing, and at that point you're able to control the flash memory. You're able to control the module without BDM. Okay, you're doing it by sending commands over the transmit and receive lines, which will be labeled as CAN. Okay, because that's what they appear to be, but they're not CAN. These are not CAN bus commands. All right, these are transmit and receive individual bits of data, and there are a variety of what are called protocols, which can be sent over these lines in order to communicate with the microcontroller. You can do it with an ASCII protocol. You can do it with an SPI protocol. There's a variety of them. But I wanted you to understand this, all right? Because this is not a front door. This is not the back door, which is what BDM is. I called it the side door because it's like, halfway, okay? So that's what I wanted to cover regarding the boot mode. And in order, as I said before, in order to enter boot mode, you've got to have a ground connection on the boot pin, okay, when you apply power to the processor. Because when the processor starts, one of the things that it's going to do when it starts, it's going to go out and it's going to sample the boot pin. It's going to look and see what the boot pin is, okay? And if the boot pin, normally my pen's not writing, the boot pin is at ground, then it's going to enter boot mode expecting a bunch of instructions to be uploaded over whatever the interface was where they programmed. Believe me, there's a bunch of different options for engineers to choose in the microcontroller. But fundamentally, when it's in boot mode, after it enters boot mode, you're going to take the ground pin away, and the processor's going to be sitting there waiting to do something, waiting to get that data coming in. And then the data comes in from the program that's in the tool. It goes into RAM, and after it's all loaded up, the microcontroller then starts executing the program from RAM. Okay, from RAM. Once you've done all of all of the activities and procedures you want to do, when you're going to read, backup, program, whatever you're going to do, okay, and you turn off your power supply here, this goes away. The program disappears, and you are no longer in boot mode. Okay, so unlike BDM will always be there when you start. You don't have to do anything. Basically, you just start sending BDM commands. But boot mode, you have to upload a communication program into the part. Do whatever you want to do, and then when you're finished, you disconnect it. The program vanishes from RAM because random access memory is what's called volatile memory. The contents goes away when power is removed. So that's boot mode. As a side door, that's how it works.